Section 1.2, the language of sets. So when we're going to talk about sets, there's a number of ways we can express them. So first of all, a little notation here. If you see this symbol, which looks a little bit like an E, that means that the element X is in that set S. And if there's a cross through it, as you can see here, that means X is not an element in S. A common way of writing sets is using set roster notation. That's when we basically list the elements, usually between squiggly brackets. And we can use ellipses if it's quite a long set. As a reminder, if you see the ellipses like we have here without a number, then we assume it does keep going. So this would be the set of positive integers. We've got something called the Axiom of Extension, which says that the set is completely determined by what its elements are. In other words, the order does not necessarily matter. It's okay if something is listed more than once as well. All right, so let's just practice using our set roster notation. So here A is 1, 2, and 3, B is 3, 1, and 2, and C is 1, 1, 2, 3, 3, and 3. So what are the elements of each of those sets, and how are they related to each other? We would say that A, B, and C all have the same elements, 1, 2, and 3. They are essentially equal. They are just different ways of representing the exact same set. So B is going to start looking strange. We've got a 0 with the squiggly brackets around it, and we want to know, is that equal to 0? Our answer to that is no. If there's no squiggly brackets, as we have on the right, then it's just a number. However, if we have squiggly brackets, then it is a set. A set cannot be equal to a number, even if that number is part of the set. So that might sound a little tricky, but that is what our notation is. Our next one, we've got the set 1, comma, and then I've got 1 in squiggly brackets. How many elements are there in that set? We would say it has 2 elements. 1, and then the set whose only element is 1, which is the second one where I have 1 in squiggly brackets. And finally, we are saying for each non-negative integer n, u sub n is the set n comma negative n, and given that we'd like to find u1, u2, and u naught. Do note we usually say not if that subscript is a 0. So u1 would be 1 and negative 1, u2 would be 2 and negative 2. Now technically u naught is 0 and negative 0, but of course negative 0 doesn't change anything. And we could write it with 2 zeros, but since there is repetition there, we would generally write it as just the 1. All right, let's talk about some of our very common symbols. The set of real numbers. Now, when you go online and do the homework, you will usually see it as a bold R, but when we have to write things, you will see it as think of it as an outlined capital R. The capital Q, that is the set of all rational numbers. A capital Z, that is the set of integers. It's from the Latin, if you're curious where the Z comes from. And finally, the capital N is the set of all natural numbers. And we will see each of those symbols pretty frequently, so we do want to know what they stand for. All right, so we often are going to see superscripts to clarify details. So a very common one might be this R with the plus, so that would indicate we're in the real numbers, but only in the positives, because of the plus. If we have our integer symbol Z, and then non-neg up there, that would be all of our non-negative integers, which does, of course, include 0. Do note non-negative integers, as far as I'm concerned, are different than the natural numbers. I would consider the natural numbers to be just the positive integers, in other words, not including 0. We can express the set of real numbers as points on a line, our number line. We've got that 0 in the middle, which is the origin, and of course we can go right for positive and left for negative. So here is that number line, and we can see what it looks like. We usually start with the integers because they're easy, but we certainly can put in there rational numbers, irrational numbers, and so on. All right, let's look at something called set builder notation. Now we are still going to put little curly brackets around this, and we're going to have two things. We first are going to use this element. So I'd read this part as x is an element of S. This straight up and down line I would read as such that. And then after that we'll be given some sort of statement for which this will be true. And here we're just going to write p of x because we don't have a statement to look at yet. You can write these in the other order. I will generally put what the set is as the first one. So let's look at that set builder notation. So remember, r is the real numbers, z is the integers, and that z plus then would be the positive integers. So let's describe the following. So here is my first notation, and I would read that as x is in the real numbers, or you could just say x is a real numbers, such that x is between -2 and +5. On our number line, I would then shade those middle parts, and you'll notice I have open circles at the end because we are not including those endpoints. Now, b is going to look very similar. The only difference now is instead of the real numbers, I've got the integers. So, this is not the numbers in between. And again, we're not including the endpoints, so this is just going to be -1, 0, 1, 2, 3, and 4. So there's a lot less going on there. And finally, C, again, looks almost the same. The only difference is I've got this little positive sign here. So again, that is positive integers only. So, looking at part B, we only want the positive answers from that list. So my answer would be 1, 2, 3, and 4. So make sure that you are looking what numbers are we using, because that is going to make a big difference in our answer. All right, let's talk about subsets. So, first of all, our notation looks like this. It looks a little bit like a less than or equal to sign, except more curved. So I would read that as A is a subset of B, and we would say that is true if every element in A is also an element of B. And if we describe it that way, so again, if x is an element in A, then x will also be an element in B. And again, we could also say is contained in. And if we want to say something is not a subset, we're going to put that little cross line through it, and that would mean that there is at least one element, x, where x is in A, but x is not in B. Finally, we do also have something called a proper subset, and that is where every element of A is in B, which is the same as a regular subset, but then there's also at least one more element of B that's not in A. So in other words, B is bigger than A. They cannot be equal to each other. They can be equal to each other if they are just regular subsets as opposed to proper subsets. All right, well, let's take that and look through some examples. So A is the positive integers. B, n is an integer such that n is between 0 and 100, and we are including those endpoints. And then C is 100, 200, 300, 400, 500. So we've got a whole bunch of statements here, and we would like to say if they are true or false. So again, just to read that, I would read B is a subset of A, and that is false because 0 is not a positive integer. So in other words, I have a value in B that is not in A. So we would put that little slash symbol through that. C is a proper subset of A. So again, that means everything in C is in A, but there's more in A. That is true. For example, 1 is in A, but it is not in C. C and B have at least one element in common. That is true. They both include 100s. My next one, C is a subset of B. That is false. 200 is in C, but it's not in B. And finally, C is a subset of C. This is true. And generally speaking, if you've got subsets like that, a set is a subset of itself. So we can do that pretty much all the time. All right, now some of our tricky notation is these two symbols. So as a reminder, that first symbol means this is an element that is contained in the set, and the second notation is for subsets. So number A, 2 is an element of the set 1, 2, and 3. That is true because 2 is in there. Now B, I've got it almost the same, but I've also got the curly brackets around the 2. So I'm saying the set 2 is an element of this set. That is not a true statement. And in order for that to be true, that second set would have to have curly brackets around the 2, which it does not. Number 2 says that the element 2 is a subset of the set 1, 2, 3. So this 2 is not a set, so it cannot be a subset then. Yeah, that's just bad notation on that one. Number D, the set 2 is a subset of the set 1, 2, and 3. That is true. So here this is a set, the other set is also a set, and the set on the right does contain 2. E is where it's getting tricky. I've got 2 with curly brackets, the subset sign, and I've got a set on the right, but each one of those, you'll notice, then also has curly brackets around it. Really the difference between E and F is one of these, E, has the subset symbol, but F has the element of. And as you can see, F is the true statement. And, oops, where it goes down. Oh, I didn't actually write out the solution to that. The reason E does not work is because we've got sets inside of sets. Because I've got the sets inside of it, the reason F is working is you can have that set as an element because my set on the right, those elements are themselves both sets. All right, let's talk about Cartesian products. So this is basically for an ordered pair. So for example, A comma B. Now in order for 2 ordered pairs to be equal, not only do the elements have to be equal, but they have to be in the same order. In other words, A comma B and B comma A are not necessarily going to be equal, unless of course A equals B. So again, that being in the correct order is an important part of this definition. So, for example, is 1 comma 2 equal to 2 comma 1? No, it definitely is not. The order matters. How about 3 comma 5 tenths equals the square root of 9 comma 1/2? That is true. Those are just different ways of writing the same number, and they're in the same order, so that is perfectly okay. And then what is the first element of 1 comma 1? Both the first and the second elements are in fact 1. I'm going to pause section 1.2 since I've run out of video, and I will pick it up in the next video.